Welcome to this course on Elements of Mechanical Engineering. In this lecture, we are going to study the working of a Kaplan turbine. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. In this lecture, we are in the second module where we are studying different types of boilers and different types of hydraulic machines. And hydraulic machines, there are two types, turbines and pumps. In this lecture, we are going to study the working of a Kaplan turbine. Now, when we see the basic construction of a Kaplan turbine, it is a very simple turbine. Like when we study the working, we can understand that Kaplan turbine is very simple when compared to Francis turbine. Francis turbine is a complex structure which is closed and all the elements inside are closed inside a casing, and the pressure inside is not atmospheric. The pressure inside the casing is very high when compared to atmospheric pressure. Now, let us see the basic definition of Kaplan turbine. So, the Kaplan turbine is a propeller type water turbine which has adjustable blades. So, this is the turbine where the blades can be adjusted based on the discharge or based on the flow of water. And it was developed in 1913 by an Austrian professor, Victor Kaplan. That is why this turbine is named after this professor. So, his name is Victor Kaplan. So, the turbine itself is named after him. So, he combined the automatically adjustable propeller blades with adjustable wicket gates. Now, we should know this terminology before going to understand what is the working of this turbine. So, there are two things: adjustable propeller blades, and adjustable wicket gates. We have seen in the previous lectures that wicket blades are nothing but these are the stationary vanes that are attached inside the turbine where they will make the water flow in a particular direction. So, with the help of these wicket blades, we can make the water, we can change the flow of direction. And whereas propeller blades are the blades that are attached to the runner, where when water touches this propeller blades, the runner will rotate. Now, this professor, Victor Kaplan, he combined the automatically adjustable propeller blades with automatically adjusted wicket gates. Now, in the Francis turbine, we have seen that whatever the blades, wicket blades are there, these wicket blades can be adjusted from outside. Like an operator can adjust the direction of orientation of the wicket blades in Francis turbine. So, in this, along with the wicket blades, we can also adjust propeller blades. So, this can be done automatically depending on the flow or discharge of water. Now, this automatically adjustable things were first introduced by this professor named Victor Kaplan. That is why this turbine is named after himself. To why he has done this? To achieve the maximum efficiency. Okay, so depending on, we don't care about the discharge of water. Even though the discharge of water is low, we can get maximum efficiency. Okay. Now, the Kaplan turbine was evolution of the Francis turbine. We can simply know that this is the development of a Francis turbine where we have adjusted the propeller blades also. Not only the wicket gates, we can adjust propeller blades. So, this is an development, or this is a modified version of Francis turbine. But there are some differences we'll try to understand. Its invention allowed efficient power production in low head applications, which was not possible with Francis turbine. So, in these turbines, we can get maximum efficiency with very low head. Okay, even the water head is very low. We know the water head is nothing but the height of water that is present inside the reservoir. So, with the low head, we can use this turbine to get maximum efficiency. Whereas in Francis turbine, we need more head in order to get the optimum efficiency at least. Now, we'll try to understand the working of the Kaplan turbine. So, see here in this picture, we can see there is a shaft this is a shaft on which we will attach a runner. So this shaft is in vertical direction. The runner is attached in this manner, and the runner will rotate in horizontal plane. And see here, these are the guide vanes. These are the scroll casings. This entire thing is called scroll casing, where water will enter this scroll casing in rotating manner. Okay, this scroll casing, this is a sectional view where we are able to see the inside parts. But when we want to see the actual working of the water that is coming from the reservoir, that is through the penstock, so the water will be rotating in circular motion while before it entering into the turbine runner. Okay, so this is a cross-sectional view. This is a spiral casing where it is a cylindrical tube which is arranged in spiral manner, where water will flow through it so that the water will gain maximum velocity before it touches the turbine runner. Okay, so after it hits the turbine, the water will be flowing downwards in this direction. The water will flow in this direction towards the bottom direction due to gravity, and from there it will be left out into the draft tube. The water will be sent to the draft tube, where draft tube is a device which is used to remove the water from the turbine. We have already seen that in the previous turbine, that is Francis turbine, where we have seen the water will not come easily on its own from the casing. Okay, after the working of the turbine, the water which is present inside the casing will not come out easily. So why? Because the atmospheric pressure is, the pressure inside the casing is not equal to atmospheric pressure. It is low. So generally what happens? The pressure inside the casing is low when compared to atmospheric pressure. Generally what happens? The water can easily flow from high pressure to low pressure. Okay. Now what happens is, we want to remove the water from low pressure to high pressure. That is why we have to design the draft tube which is attached to the turbine casing, and this draft tube is designed in such a way that its cross section is increasing. It has an increasing cross sectional area. This is a cylindrical tube where, due to the increasing cross sectional area of this draft tube, we can actually remove the water that is present inside the casing very easily, because we have temperature difference. We have pressure difference, because of which water cannot come out. Similarly, this entire thing is in the Francis turbine and as well as other types of reaction turbines. In this case, we have a draft tube which is in the shape of a rectangular cross section. See here, this is a rectangular cross section. Here, this is a circular cross section. So in Francis turbine, we will use a circular cross section draft tube, but here we will use a rectangular cross section which is attached to the casing of the turbine. Now, the function of this turbine, the function of this rectangular shaped draft tube is also very similar to that of draft tube in Francis turbine. It will easily remove the water that is present inside the turbine, and so that the water can be, the runner will produce more energy efficiently. Now let us see some numbers, like what is the head range of this Kaplan turbine, what is the runner diameters, dimensions, and different types of parameters on which the turbine will be designed or turbine can be selected. See, the first point is the head range. The head range from 10 meters to 70 meters. Even the Kaplan turbine can work for a head as low as 10 meters or 33 feet. Okay, so from 10 meters to 70 meters, this turbine can be efficiently used. And the output range, that is, generally we will use the turbine for electric production. So we will measure the electricity that is developed by this turbine. So when we compare that, the electricity that can be produced by this turbine varies from 5 to 200 megawatts depending on the size of the turbine. So smaller turbines will produce low electricity, larger turbines can produce more. So the power generation capacity is from 5 to 200 megawatts. And coming to the dimensions of runner, the dimensions of runner stays between 2 and 11 meters. Okay, 2 meters to 11 meters the diameter. We can simply understand how big the turbine is. These turbines are very large when they are used for production of electricity. So, for academic purpose, we used to install small sized turbines in our institutions, where these are very small prototypes where we can understand the working of these turbines. The turbines rotate at a constant rate which varies from facility to facility. When we want to compare the speed of this turbine with which the turbine can rotate, so if we want to compare the speed, it depends on the size of the turbine. Like one turbine will have different speed when compared to other turbine. Even though both are Kaplan turbines, they will have different speeds. And the rate range from as low as 54.5 rpm to 450 rpm. So depending on the size of the turbine, the speed of the rotation of the runner varies from 54 to 450 rpm. That, as we say, it depends on the size of the turbine. Smaller turbine or larger turbine, depending on the rated speed of the generator also, we have to select a turbine of required RPM. And next, so let us see some numericals about how the discharge can be calculated for a Kaplan turbine. So this is the formula. Now we'll try to understand what are the different parameters or terminology related to Kaplan turbine. So the expressions for work done, efficiency and power developed by axial flow propeller Kaplan turbines are identical to those of a Francis turbine. So we can see in this, we have seen already in the previous lectures, the work done, efficiency and power. So all these formulas we have calculated for Francis turbine. So all those formulas are perfectly valid for this Kaplan turbine as well. But some formulas will be changed, like we have to calculate the discharge. So discharge is different for Francis turbine and Kaplan turbine. Remaining all formulas are very similar. They will have the same formula, and so we can use those formulas of Francis turbine in this case. So the only changed formula is here the ratio is changed. The ratio n is taken as dB divided by d naught. So dB is the diameter of the you can see here dB is the diameter of the boss or hub. That means this part. This is the boss on which we will connect the runner. Okay, so this is the diameter of the boss or hub, and DO is the diameter of the runner, like outside diameter of the runner. I will draw this simply. If this is a runner, this is in the circular shape. At the center, we will connect a cylindrical rod that is called as boss or hub, which is used to hold the entire runner structure. So the diameter of this boss is taken as D suffix B, and the diameter of this runner, the outer diameter of the runner is taken as DO, D outer. So this ratio dB by d naught is the ratio we have to use in the calculation of discharge. Now when we try to calculate the discharge of this Kaplan turbine, so it is simply area of the flow multiplied by velocity, A into V. Area of the flow multiplied the velocity of the flow. Okay, this will be given by, we can simply use this diameters like d naught and dB can be used to calculate the area, that is pi by 4 d square, where we will have two diameters, the diameter of the boss and the diameter of the outer periphery of the Kaplan turbine's runner. So, and Vf is the flow velocity of the water that is being entering into the casing. Okay, now using this formula, we will rewrite the flow velocity as Kf multiplied by root over 2gh, where g stands for gravity and h stands for head. And from this we can calculate Q is equal to, this entire formula is calculated, pi by 4 d naught square into 1 minus n square multiplied by k suffix f root over 2gh. Okay, so this is the formula for discharge of water that is coming out of the turbine, like Kaplan turbine. Now we have some more points to understand when we study a Kaplan turbine. So let us try to understand the second point, that is the periphery velocity u. So this is the velocity that is denoted with letter small u. We'll try to understand what is the thing about this velocity. So the peripheral velocity of the runner depends upon the radius of the point under consideration, and thus the blade angles vary from the rim to the boss and vanes are wrapped. This is necessary to ensure shock-free entry and exit. So we'll try to understand this sentence with the help of this graph. So when we want to calculate the peripheral velocity, that is the velocity of the runner on the outer periphery, if we want to calculate that velocity, we have to consider two things. It totally depends on the radius of point where we are considering. Okay, where we are considering that point, particular point, with respect to that point we are calculating the radius. We are calculating the peripheral velocity. Okay, and also blade angles. Blade angles are also considered while we are calculating this velocity. So based on this radius and velocity, the peripheral velocity is calculated. Now see here, we have third point. The velocity of flow remains constant throughout. So whenever we take a graph that is between efficiency and full load percentage, this is efficiency and this is full load. So we can see this curve, this violet color graph shows that the velocity of the flow remains constant throughout the process. Okay, and this figure shows the comparison of efficiencies of propeller and Kaplan turbine. Okay, when we want to compare the efficiencies of a fixed blade propeller turbine and a Kaplan turbine, so we can simply see the Kaplan turbine will have more efficiency because the Kaplan turbine has movable blades. The blades on the propeller can be movable and they can be adjusted according to the speed or discharge of the water. Okay, that is why we can attain more efficiency when compared to a fixed blade type of turbine, that is Francis turbine. Now, so far we have seen the working of Kaplan turbine and we have seen different parts of it. We have seen the calculation of discharge, power, work done, efficiency, etc. So some formulas are very similar to those of Francis turbine. The only thing changes here is discharge, because we have a different type of runner and hub attachment here. We have to calculate the discharge again with those diameters in order to calculate the actual discharge of the Kaplan turbine. Now we will move to the next topic, that is cavitation. So this topic, cavitation, is very important when we are studying turbines. So we'll try to understand how cavitation happens and how danger this cavitation to the turbines and how this can be rectified or avoided. Okay, now we'll try to understand how this cavitation works. What is the phenomena of cavitation? So cavitation is one of the critical phenomena that affects hydraulic machines. We can simply see cavitation is a phenomena. Because of this cavitation, the efficiency of any hydraulic machine will decrease. It is the phenomena in which vapor bubbles form rapidly and collapse within a liquid. It mainly occurs when the static pressure becomes smaller than the liquid's vapor pressure. So because of this pressure difference between the water and the air, we can see the formation of bubbles inside the casing or inside the turbine vanes, where the pressure is not atmospheric pressure because it is a closed casing. The pressure will be varied. So because of this pressure difference, air bubbles will be rapidly formed and collapses. See here, vapor bubbles forms rapidly and collapses within the liquid. So they will form instantly bubbles these bubbles will be instantly burst out, so that this instant formation or formation and collapsing of bubbles at very high pressure inside the closed casing of the turbine. This may lead to, like we can see in this picture, this can damage the turbine parts. Okay, they will actually, we can see here, this is a picture where this is a turbine vane on which we can see the surface has been completely damaged due to the formation of this cavitation or formation of bubbles and their collapse. So these are some examples of cavitation where the turbine parts are damaged. Okay. Now here, this is a turbine shaft on which we can see, this is a turbine shaft on which we have different vanes connected here. So these are all the vanes. So we can see here, the surface is damaged. Even though this is made up of metal and this will be working under a large amount of water, the water directly may not cause any damage to the surface. But due to the formation of these bubbles and their rapid collapse, the surface is being damaged very rapidly, and this may lead to malfunctioning, and sometimes they may cause breakage of the mechanical parts of the turbine. And in the third picture, you can see this is a turbine runner on which vanes are completely eroded. All these vanes are completely eroded and they are no longer usable. So all this is happening not because of some type of corrosion. Generally, the corrosion will be seen when these metal parts are subjected to oxidation. Here, that oxidation is not happening because entire thing, the turbine and its parts are covered inside a closed casing where they can be used to produce power. And the only thing that is touching these turbine parts is water. So water itself does not cause any harm because it is a stable liquid, stable form of liquid. And the only thing that is causing damage or causing this cavitation is the formation of bubbles, that too at a very high pressure. So normal bubbles at atmospheric pressure are not dangerous, but at very high pressure inside the cylinder or inside the turbine, so they may cause this kind of damage to the turbine parts. Okay, eventually these turbine parts has to be removed or replaced with new one, so that they can be used for the production of electricity. Okay, so this is all about cavitation. Now see, we'll try to understand deeply what about cavitation. So the liquid water changes its state from liquid to vapor when we keep the pressure constant, say 1 bar, and increase the temperature above 100 degrees Celsius. Now we'll try to understand this. First point, the liquid water changes its form of liquid from liquid form to vapor. Okay, see here. Here liquid is rapidly being converted into vapor. Here we can keep the pressure constant, say 1 bar. Here the pressure is kept constant at 1 bar and increases the temperature above 100 degrees Celsius. Now you may get a doubt that how these bubbles are formed, because the entire thing is closed, like turbine is covered inside a closed casing where the pressures are completely different from the atmospheric pressure. How air from outside is entering into the water. So for that we can understand that when the temperature inside the turbines reaches about 100 degrees centigrade, we can see the formation of vapor, that is a gaseous state of water. So due to the formation of this vapor, we can see the formation of bubbles, but as we can see, there will be a difference in the temperature at different places. When the temperature is very high, vapor can be formed, and when the temperature cools down, this vapor can again be collapses and forms water particles again. Now, due to the formation of this rapid bubble formation and rapid collapsing of the bubbles, this is the reason causing the cavitation. Okay, they will increase the pressure at a particular area instantly to a large value at a very small span of time. Okay, so further, it can also change from liquid to vapor if the temperature is kept constant and the pressure is reduced below the vapor pressure. So there is another condition where we can see the formation of vapor. That is when we can keep the temperature constant. We can keep the temperature constant and pressure is reduced below the vapor pressure. When we reduce the pressure of the water below the vapor pressure, we can see the formation of vapor, that is gaseous state. Water is converted into vapor. This phase transformation of water particles will cause cavitation. So the general phenomena of conversion of water into vapor is, while if we increase the temperature of water, it will be converted into vapor. Now, if we keep the temperature constant but increase the pressure, that is at a very high pressure, water can be converted into vapor, and this vapor can be seen as a formation of bubble, and due to rapid change in the pressure, these bubbles will collapse and they may cause cavitation. And water bubbles form when the local pressure goes below the vapor pressure. So whenever the pressure is below the local vapor pressure, we can see the formation of bubbles. They may not remain in the state for long. Once the vapor bubbles reach a location where the local pressure is above the vapor pressure, they will collapse back into liquid form. So this is where we are explaining the phenomena of formation of bubbles due to change in the pressure. Here we have kept the temperature constant, but we have changed the pressure, like the pressure inside the closed casing is different. So at some points the pressure will be very high where the water will be converted into vapor, and at some other points when the water reaches some other point, it will rapidly be cooled down and converted into water again. So this can be called as cavitation, and this due to cavitation we have to face severe issues like damage to the turbine casing and turbine vanes. So these are some of the effects of cavitation. We can see in this picture, we can here see there is a micro crack that is being produced on the surface of the turbine part due to the formation of bubble. In the right side, here we can see the formation of bubble and its collapse. So initially this is a bubble and now it is collapsing. By collapsing, it is creating some kind of pressure on the surface. Now here we can see on this surface, we can see the damage, like the metal part is being removed due to increase in the local pressure. Okay, so this is the formation of bubbles and its rapid collapse, due to which we can see the phenomena of cavitation. So we can understand from this picture, microjets are powerful enough to damage even high strength material. So this is the basic thing we have to infer from this figure or from this concept. So microjets, even though the jets are very small, what is a jet? So this microjet is being emitted from the collapsing of the bubble. See here, this bubble being collapsed here. So the water bubble is collapsed and it creates a microjet. This microjet will hit this surface, which may cause damage to a high strength material also. Implosion releases packets of energy in short duration, concentrated at a microspot. It gradually leads to cavitation, corrosion, and cavitation damages. Okay, due to the formation of these microjets, that is caused due to the formation of bubble and due to its collapse, this microjet will cause damage on the surface. Over time, the material develops cracks with repeated bursts and which eventually breaks off. So if this surface is being subjected to multiple microjets, small sized cracks will form on the surface. They may lead to ultimate failure. So that this metal part will no longer can be used for the working of the turbine. So let us see some effects of cavitation. So it will produce an unsteady and trigger low frequency pressure oscillations and high frequency pressure pulses. So these are all the effects of cavitation. They can produce low frequency pressure oscillations and high frequency pressure pulses. So due to this, we can see the shaking of the turbine, or we can observe the vibrations being created inside the turbine. So this is all because of the cavitation. Okay, so cavitation is a very important phenomena where we have to study this cavitation in order to get maximum efficiency. Otherwise, the metal parts, that is the turbine vanes, turbine casing, etc., may be damaged due to the formation of cavitation. Okay, the pressure oscillations are due to high cavity dynamics, while the pressure pulses are associated with cavity collapse. So we can see the formation of vibrations or pressure pulses due to the collapsing of bubbles. And these sources of excitement that act inside the main flow or adjacent to the walls generate vibrations and acoustic noise. So we can hear the cavitation. Generally, the cavitation can be heard in the form of vibrations or in the form of noise. Okay. So this is where we can practically observe the formation of cavitation. And then when they propagate through hydrodynamic and mechanical systems, it results in high vibrations. Whenever these propagate, whenever these hydrodynamic and mechanical systems, the cavitation as propagates, they may result in very high vibrations, blade erosions and instabilities, ultimately leading to the destruction of the whole machinery. So the formation of these microjets may lead to cracks, and ultimately they will lead to damage of the entire structure or entire machinery. So cavitation is very bad thing. So we have to avoid it in somehow, any manner. Like we'll see what are the types of cavitation. There are different types of cavitation where we have to study in order to understand how to control them. So the first one is leading edge cavitation in turbines. We'll try to understand what is leading edge cavitation. This type of cavitation is usually seen attached to the runner blade's suction side. They are formed under operating conditions of high head and inflow incidence angles that are positively larger than the design value. See here, this phenomenon, that is leading edge cavitation, is seen on the pressure side, like on the suction side of the runner blade. Okay, on which side we can see the suction pressure. So on that side we can see this type of cavitation. They are formed under operating conditions of high head and they are positively larger than the design value when the head and inflow, okay, when the head and inflow angle, that is alpha, when these two values are very high when compared to the design values, then we will observe this kind of cavitation. H stands for head, that is when the head is very high, that is more than the design value, and alpha, that is the incidence angle. When the incidence angle is more than the design value, we can see the formation of this leading edge type cavitation. And also they can also occur on the pressure side when operating at a low head and negative angle of incidence. Okay, these can be seen on the other side of the runner where the entire machine is being operated at low head or negative angle, like these two. When these two are high, like a high head, and this is positive, we can see the leading edge cavitation on the suction side. And if this head is low and alpha, that is leading edge angle, is negative, then we can see the type of cavitation on the other side, that is the other side of the turbine, not the suction side. Okay, so due to this formation of cavitation, we can see the fluctuation of speed. The turbine runner may not rotate easily. That means the fluctuation of speed will be observed. Due to this, we can see the decrease in the efficiency. And then this is second type of cavitation, that is traveling bubble cavitation in turbines. So see here, they take the form of separated bubbles attached to the blade suction side near the mid chord right next to the trailing edge. We can see in this picture, this is a hub or the shaft that is attached to the runner. Okay, now we can see here there is a formation of bubbles. You can see formation of bubbles here. These are all vanes. Okay, so in traveling bubble cavitation, we can see the formation of bubbles at the center, like near the shaft or hub. These bubbles will travel along the vanes in this direction, and finally they will reach the outer periphery. Okay, so they are formed due to low plant cavitation numbers, and they tend to gradually grow and increase in load and attain maximum size when the machine operates in overload conditions with maximum flow rate. So how does this cavitation bubbles will form? They will form due to a condition where the turbine is being overloaded. See here, the turbine is being overloaded. That is, the maximum amount of energy is being removed from the turbine. That means we are using the turbine for the production of more electricity. Then we can see this kind of cavitation that is being developed in the turbine. So this is very dangerous for the turbine parts, because bubbles will be formed at the center. That is, when the turbine is rotating at a very high speed, more than the rated RPM, then we can see the formation of bubbles at the shaft or the hub, and they will travel along the surface of the vanes, and finally they will collapse at the edges of the turbine, which will cause damage to the vanes and also damage to the casing. So because of this, this phenomena can be seen when the turbine is being overloaded. So these are very severe and noisy types cavitation that provoke blade erosion and significantly reduce the machine efficiency. So this kind of cavitation is very dangerous. They can erode the blades, and also they will reduce the machine efficiency, which is not required at all, because the efficiency has to be maximum as high as possible, and the blade parts or the blades, vanes, the turbine parts should have a maximum life as long as possible. And then there is third type of cavitation, that is draft tube swirl. So in this picture we can see this is a draft tube swirl. That means we know the draft tube is the device which is attached to the casing to remove the water from the turbine casing. Okay, so what happens inside this draft tube is, when the water is continuously coming out, we can see in some types of turbines the water will be rotating in a spiral motion. Like we have seen in Kaplan turbine, the water will be entering into the turbine in a spiral manner. So due to this, we can see the water will be rotating in a circular motion while it is coming out of the draft tube. So due to this, we can see the formation of swirl, or we can see the formation of vortex. Okay, so when the water that is coming out of the turbine, we can see the formation of a vortex. Okay, this vortex is where the pressure will be low when compared to the other regions. Okay, so in this red colored part, like I have highlighted this part, so this point, this area is called as vortex. In vortex, the pressure is very low when compared to other parts of the water. This is all water, entirely filled with water. The water is rotating in circular motion, where we can see the formation of a vortex. But at vortex, the pressure is very low when compared to other regions. So this may also cause a type of cavitation. Okay, how this will happen? So the vortex appears in partial load and overload conditions. So we can see the formation of this vortex when a partial load is being applied on the turbine, or the turbine is being overloaded. Due to this residual circumferential velocity component, the flow discharged from the runner. Okay, so due to overloading or partially loading the turbine, we can see the water will be rotating in this direction, and we can see the formation of vortex. This vortex will, where the pressure is very low, it may cause a cavitation that is called draft tube swirl. And in some instances, they generate large bursts of pressure pulses in the draft tube, causing strong vibrations on the turbine and even on the powerhouse. Okay, we can see large amount of water that is coming out of the draft tube. Okay, draft tube, after water entering into the turbine, the water will come out of the draft tube. When this water that is coming out of the draft tube is rotating at a very high speed, it will form a vortex. This vortex is very dangerous, like it can shake the entire turbine power plant, or it can damage the draft tube. Even the draft tube is a very important part, where it is designed in such a manner to remove the water easily from the turbine to the tail race. Okay, so the water, if the cavitation it creates large amount of pressure vibrations inside the draft tube. The draft tube may break, or the draft tube will be detached from the turbine casing. So this may cause a catastrophic failure where the entire turbine is no longer used for the production of electricity. So this draft tube swirl has to be it should not be happened. So we have to take necessary measures in order to avoid the formation of draft tube swirl. So by studying these different types of cavitations, we can understand how to stop them. Okay, in this case we can see when the machine is partially loaded or overloaded. See here, partial load or overload. So we have to see that the machine should not be partially loaded or overloaded. It should be loaded at a optimum manner. Okay, then this draft tube swirls will not form and they may not cause any damage to the turbine. And when we go to the second type of cavitation, that is traveling bubble cavitation. So this is seen due to the formation of increase in the load. Okay, due to increase in the load on the turbine, we can see the formation of this kind of bubbles. So these bubbles will travel along the vanes and they will collapse. So we have to see that the machine should not be overloaded. Okay, it should not be overloaded so that it will run at optimum designed pressure, optimum designed RPM. And here, in this type of leading edge cavitation will be seen when there is a high head and the incidence angle is positive or negative. Okay, we have to maintain this in the optimum value so that they may not cause any type of cavitations. And we have another type of cavitation here, interblade vortex cavitation in turbines. So see here, we have vanes. These are all vanes which are attached to the runner, and when the runner is rotating, all these vanes can rotate and they will produce some movement of the water. So due to this movement, we can see the formation of bubbles. These are all bubbles because there is a here the pressure is more than the vapor pressure. They will form they will form bubbles. Okay, the water will be converted into vapor. So due to the formation of this vapor, these bubbles after collapsing, they will cause penetrations on the surface of these vanes. Okay, so due to this, we can see the formation of cavitation. So cavitation is a very bad scenario where we have to stop this cavitation using some predefined methods like running the machine at optimum values, whether it is head or speed or load, anything has to be run at optimum values. Otherwise, they will cause bubbles and their collapse, and finally they will cause cavitation. And this cavitation is so dangerous that the entire machine parts will collapse and they will break. Okay, the machine will no longer be used for the production of electricity. So this is all about cavitation. And in this lecture, we have seen the working of Kaplan turbine and some numericals. And also we have seen cavitation and types of cavitation, and also methods how to stop cavitation, the formation of cavitation, and how to avoid it. Okay, by running the machines at optimum values. So that is all for this class. We'll meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.